Hey, how's it going? So for this module topic, we'll be looking at compound interest. So when it comes to compound interest, when it comes to Algebra 1, on the formula sheet, you will have compound interest formula given to you. It's right here at the bottom. But more important than having it on the formula sheet is understanding what it represents. So at this point, we've already looked at exponential functions. All right. So you've seen exponential functions in this format where you have where you have your initial value, and then if it's increasing, you'll put 1 plus the rate, and if it's decreasing, you'll do 1 minus the rate. Instead of increasing and decreasing, you might often hear it as growth and decay. But there's various terms that can be used instead of increasing and decreasing when it comes to exponential functions. Now, bringing it back to compound interest, you would utilize this compound interest formula only when interest is being compounded multiple times in 1 year. So if it's only being compounded annually, like once a year, you would just go ahead and use the formulas for writing the exponential equation. But if it's being compounded, let's say monthly, which is 12 times a year, or weekly, which is 52 times a year, and so forth, then you will use this compound interest formula. So now let's go ahead and discuss each aspect of this compound interest formula. P is your principal. That's whatever your initial value is, very similar to writing a regular exponential equation. You're always going to have that 1 there. And then because when it comes to compound interest, it's going to be always increasing, you'll put plus. But we know that an exponential function can be decaying, so we will put minus in that context. But when it comes to compound interest, it's always going to be growing, so that's why I'll be plus here. And then we'll have the rate, like we traditionally have in an exponential equation. Now the new piece of it, number of times interest is being compounded per year. That goes in 2 different places. It goes right below your rate, and it goes in your exponent. So if it's being compounded, let's say semi-annually, which is twice a year, you would put 2 underneath the fraction here, and you would put 2 in the exponent times t, which is the number of years it's being compounded. So that exponent in total, when you multiply that exponent, that's telling you in total how many times is it being compounded. Because let's say it's semi-annually and it's 2 and it's 10 years, this 2 times 10 will give us 20. So that means the interest is being compounded 20 times over that span. And then A is your final result. So before we look at our first example, we got to discuss annually, semi-annually, and so forth. Annually means it's only being compounded once per year. Semi-annually means twice per year. Monthly, you got 12 months in a year. Quarterly, think about how many quarters in a dollar, which is 4, so that's 4 times a year. Daily, you would use 365. Assuming, I know sometimes it's a leap year every 4 years, but if they say daily, they're going to be assuming that you're just referencing 365 days. And for weekly, it'll be 52 weeks in a year. Now let's go ahead and look at our first example. Daniel deposits $800 into a savings account that has a 4.2% interest rate annually. What will be the balance of Daniel's savings account after 9 years? So let's go ahead and break down each aspect here. P, the principal, which is 800. The rate, that's 4.2%. You need to convert that to a decimal. So you can either say move the decimal to the left twice, or you can say divide by 100. Because if I took 4.2 and divide it by 100, you get 0.042. When you put a percent inside of an equation, you have to convert it to a decimal. Or you can say before you put a percent into an equation, you have to take that percent and divide it by 100. All right. The tomato, either way, they both mean the same thing. All right. So then we have 0.042. Reason I want to make sure I harp in on that, the most common mistake here is that we'll just put 4.2 in for the R and not that 0.042. But let's keep moving. N represents the number of times it's being compounded each year. Annually means once a year. And then T represents time. That means how many years are we looking at this being compounded? That's going to be 9 years. So we go ahead and plug this into our equation. So yeah, you could just plug this into Desmos and get your result, right? But I want to simplify this so I can show you that this is the same thing as a traditional exponential growth and decay equation. If it's annually, 0.042 over 1 is the same thing. It's having just 0.042. 1 times 9 is just 9. All right. So if it's annually, you don't necessarily need to use the compound interest formula. Only when it's being compounded more than 1 time per year, then you would use this formula. All right. So then you could type in either one of these and you should get the same result, which is $1,158.51, as you can see over here. So let's go ahead and look at our next example. Jasmine deposits $520 into an account that has a 3.5% interest rate compounded monthly. What will be the balance of Jasmine's savings account after 2 years? So let's go ahead and break it all down. We see that it says monthly. That's more than one time per year. So that means we're going to use the compound interest formula. So then P, which is the principal, is 520. The rate, we got to convert that 3.5% to a decimal. We had to take that 3.5 and divide it by 100, and we should get 0.035. And how many times is it being compounded each year? Monthly is 12. So we'll put 12 in 2 different places. And then how many years is being passed? It's going to be 2 years, so T would be 2. So from here, you go ahead and plug it in, and then type it straight into Desmos. Yes, I know you can do this manually, but why do it manually when, at least in Georgia, you'll have Desmos on your end of course test? Pay attention to how I type this in, though. Notice that I put parentheses here over 12 and then around 2 as well. Because if you type in raised to 12 times 2, it drops down here. All right, so that's why traditionally when you put it in the exponent, I'll go ahead and put 12 close parentheses 2, just so you don't mess around and put times 2 quickly, and then it just doesn't put it in the exponent and you get the wrong answer. So I would always put it in parentheses, even though mathematically you don't have to, but just a tip of how to utilize Desmos in a more efficient way. And you should get $557.65, as you can see here. So for these next 4 examples, I'm going to go through a little quickly, but just want to practice in regards to how to go ahead and fill in this equation over here. So when we look at this example, if the principal is 12,000 and the interest rate that is growing is 12.7%, and you want to calculate the amount of this investment above after 5 years with interest compounded quarterly, that's enough information to go ahead and fill this in. The principal is 12,000. The interest rate is 12.7. So we have to take 12.7 and divide it by 100. And we should get 0.127. And then how many times is it being compounded each year? Quarterly, 4 quarters in a dollar. So that'll be 4. And how many years? It'll be 5. So from here, we'll go ahead and plug those values in. And once you plug those values in, you should get $22,421.82. Remember, go ahead and put these exponents in parentheses so you don't have to keep manipulating Desmos in order to keep the values in the exponent. All right. So in our next example, if you deposit $6,500 into an account paying 4.8% interest compounded daily, how much money will be in the account after 3 years? So the initial value is going to be $6,500 or $6,500. The interest rate is 4.8%, but we don't put 4.8. We take that and divide it by 100, and we get 0.048. And then how many times is being compounded each year? That's daily. That's 365. So I got to put that in 2 places, underneath the fraction and in their exponent. And then it's 3 years. And then we just go ahead and type this into Desmos. And our result should be $7,506.68. Our next example, you starting off with $5,000 here, 8.25% interest rate. So we got divided by 100 and get 0.0825. And it's being compounded semi-annually. Semi-annually is twice a year and for 7 years. And once you type it into Desmos, your result should be $8,805.22. Now, I want to go ahead and get to this problem here. I'm going to take a little time with this one because now this is a problem that's written a little differently, but it's the exact same structure. This problem reads, Lex had $1,780.64 in her savings account that she opened 6 years ago. Her account has an annual interest rate of 6.8% compounded weekly. How much money does Lex now have in her savings account? So you're trying to figure out how much she has now, and they're saying that she initially started with $1,780.64. So that's still your principal that goes out front. And then it says it's going to take, it's 6 years later, right? So if it's 6 years later, that's that T up there. And then it's weekly, so that's 52. And then the interest rate is 6.8%. So we had to divide that by 100 and get 0.068. So we have all the information. Now it's just the problem was stated like going backwards. All right. But it's still the same structure in regards to how we find the result here. So then now you'll go ahead and plug those values in like we did in the previous several examples. And our end result should be $2,677.03. So how much money she has in her account currently is $2,677.03. All right, so now it's time to practice.